Last time we met, we were talking both about qualitative and quantitative ways of looking at solutions. And I want to go back just for a little bit about those qualitative or those qualitative ideas of solutions. And one of those is the idea of a saturated solution versus a concentrated solution. Saturation refers to the maximum amount of solute that can be dissolved in a particular amount of solvent under certain conditions. So saturated solution is in reference to what's called solubility. Let's see if I can't spell that correctly this morning. Solubility. Solubility limit or a saturated solution is one in which the maximum amount of solute has been dissolved into a particular amount, oh my goodness, of solvent under specific conditions. And really, that's talking about temperature. Concentrated solution is a little bit of a relative scale. So a concentrated solution one in which a lot of solute has been dissolved into solution. Maximum concentration is the same as the saturated solution. It is entirely possible to have a concentrated solution that is not saturated. For example, HCl gas it actually reacts with water, but we can think of it as a dissolution. So the maximum amount, a solution that is saturated in HCl, is what's called is has a concentration of 12.5, and then here's a new unit, molar. It's just a way of expressing a concentration. I shouldn't say we consider, I consider. I consider HCl solutions of, I would say probably 3 molar and higher to be concentrated. Obviously, the closer that I get to this 12.5 saturation, molar saturation point, the more concentrated it is. How does a solution form? This is probably one of the last times we're going to be really mentioning intermolecular forces in a formal way as part of lecture. If I think about what happens when a solution forms, let's think about, I've got a solute and then I have a solvent. My solvent molecules, and we're going to work on liquid. Okay, so I've got these bluish circles here of solvent molecules, for lack of a better way to draw them. And remember, between them, we have these intermolecular forces. So those are the funky little dotted lines. So IMFs between solvent particles. And then solute, I'm gonna circle those in. For the sake of this drawing, I'm doing liquid, liquid, but this is any condensed phase solution. So a solvent being liquid and a solute being solid. And I'm just willy-nilly, randomly putting together these intermolecular forces, right? So I have these IMFs now between the solute particles. Now I'm going to be making a solution. In that solution, I'm going to have not only hopefully somewhat random looking, I'll have the solvent, and then I'll also have those solutes. In order to go from pure solute and pure solvent, I need to have, come here, these new intermolecular forces form between solvent and solute. Once again, just doing a very rough sketch of, all right, just a really rough sketch of this idea of these particles playing with each other here. So in solution, and new IMFs between, oops, I knew that didn't look right. There we go. Between the solute and solvent must form. So we need to break the solvent to solvent IMFs maybe not break, but overcome so IMFs. You can almost think of it as a 3-step process. They all are concurrent. So IMFs between solvent particles are overcome. IMFs between solute particles must be overcome. Then we have new IMFs between the two different parts of the solution, solute and solvent must form. If the IMFs formed aren't sufficiently strong, then the solution won't form. I'll go back and I'll think about, for example, like a 6th grade dance, middle school dance, intermediate school dance. Where you have a group of boys that hang together. Okay, so this group of boys are just hanging out, shooting the breeze, interacting. You have a group of girls, they're interacting. In middle school, intermediate school, what about the interactions between the boy group and the girl group, or between the individual boys and the individual girls? There were a few. Okay. There were some precocious boys and precocious girls that would interact between each other. But as a general rule, the solvent gang would hang by itself and the solute gang would hang by itself. Get into a little bit older teen years, into the 20s. What happens? All of a sudden, the interactions, the attractions between the two groups become stronger. So you get this mingling between the two groups. If the solute molecules and the solvent molecules don't interact strongly, then they're really not going to make a solution. Only once we start to build in these interactions between the solute and the solvent do we get that solution to form? Okay, so the key thing is we're overcoming IMFs within the solvent, overcoming interactions between the solute, and then we are making new IMFs. If the new IMFs aren't strong enough, no solution. Or the solubility will be really low. Not a lot of the solute will dissolve into the solvent. So that is an alternative. Or the saturation concentration, the concentration of the saturated solution is very low. So not a lot of the solute will get dissolved into the solvent. Let's take a moment and talk specifically liquid solutions. And the term that describes how liquids solutions are formed is actually built around this idea of what's called miscibility. So it's really it's another way to think about solubility. We tend to think solubility in terms of how many grams of solid I can get to dissolve in 100 milliliters of water, for example, or 100 milliliters of ethanol, or 100 milliliters of hexane. Miscibility is the same idea. It's just how many milliliters of benzene can mix in 100 milliliters of water. So it's a way of describing the amount of solution that can be formed when two liquids mix. And instead of mix, So if we combine them in a single container, all right, so we really have three options. One is miscible, and those miscible substances, they mix together completely. So two liquids mix in any proportion completely. So that's the idea of um, total, uh, yeah, total single phase mixture. The second one would be partially miscible. The two liquids mix to a small extent. Meaning that some of the solute actually does dissolve in the solvent. So a small amount of solute mixes into the solvent. So the solute liquid is not highly soluble. Some of it does dissolve, but not a lot. The third one, we're going to reach a point where so little of the solute goes into solution, we might as well say none of it goes in. And that's what we call immiscible. So immiscible simply refers to two liquids that do not dissolve. So the two liquids immediately separate into separate layers. Essentially, no mixing occurs. For miscible, a great example is ethanol and water. Very, very soluble. For something that is partially soluble, we would get to something like butanol. And finally, for the immiscible, vegetable oil and vinegar, which is a water solution. And I think that's all I want to talk about. I take that back. I don't want to talk about, I do not want to talk about the colloidal dispersions. I do want to talk a little bit about this notion of what's called colligative properties. And colligative properties are those properties that depend upon how many solute particles you have in solution rather than what you have in solution. So colligative properties, they're going to be physical properties that depend upon the number of solute particles in solution rather than their chemical properties. Okay, so two of them are really tied together. We've got boiling point elevation and the one that is the same idea is vapor point or vapor pressure, vapor pressure depression. Okay, or vapor pressure reduction. Remember, boiling occurs when the vapor pressure above a liquid equals the atmospheric pressure. Remember that I have in a liquid in my little container of liquid. I'm gonna draw blue. I've got particles leaving the surface of that liquid. Okay, those are vapor particles. The more vapor particles, the more vapor pressure. So here's my pure solvent. The higher the concentration, the more pronounced the effect is. Some of those solute molecules are interacting with solvent molecules at the surface. They actually are preventing some of those solvent molecules from escaping. So you have fewer particles that can escape, which means that vapor pressure will be lower. If vapor pressure is lower, I'm going to have to heat it higher and higher and higher to get a vapor pressure equal to the atmospheric pressure. So let's, for example, say that my pure solvent here, example, is essentially at the boiling point, meaning that 1, 2, 3, 4, 5, 6, the pressure caused by 6 solvent molecules is equal to the atmospheric pressure. So this pure solvent is essentially boiling. If I look at my mixture, I only have 3 vapor particles. The fact that I have fewer particles, the lower vapor pressure, means that I'm not at boiling yet. How do I increase my vapor pressure? I increase my vapor pressure by getting more vapor particles, all right? And the only way I can do that is if I excite more particles out of the mixture. I'm going to have to heat this mixture to a higher temperature. Okay, so my solution solute particles block solvent particles. From escaping into the vapor phase. Remember, vapor phase, same thing as a gas. So higher temperatures are needed to get to the needed vapor pressure. There we go. I like that. All right, so there's one is vapor. I think I always learned it as boiling point elevation. Never really talked about it in terms of vapor pressure when I was a student. It means the same thing. All right, so they're hand in hand. So that's the first of these colligative properties. All right, and again, I looped them together because vapor pressure being reduced is the reason why we see that boiling point elevation. So even though it's more commonly called boiling point elevation, we'll go from there. Okay, so the second one is freezing point depression. Okay, it is not technically true to say that salt melts ice. Well, then why do we use salt on icy roads and sidewalks? Well, it's to prevent ice from reforming. What? What? Okay, so let's talk about equilibrium. At And then this is going to be this equilibrium between the solid phase. So here's my nice, right, there's my nice solid. I'm going to get to bigger particles because I can fill them up better. All right. So here's my solid. There we go. Now, equilibrium means equal rates. Above this solid, there is a liquid. You can't see it until you get closer to the melting point. But on top of any solid, there is some liquid. Now, how much liquid? Well, if I look at, for example, my silver ring that I wear, how much liquid? Maybe one atom out of billions and billions and billions of atoms are in what we would consider the liquid phase. So I'm not going to worry about my ring liquefying and falling off my finger. Same thing with a diamond. There is an equilibrium between the liquid being formed from the solid. And again, there we go. From the liquid being formed by the solid. At the same time, liquid particles, different liquid particles, are reforming the solid state. So we have a liquid particle coming in, a liquid particle coming in. We've got a solid going to form a liquid molecule, right? Go into that liquid phase. So we've got both things going on. Equilibrium means that the rate of forming, well, let's do this. Equilibrium equal rates of forward and reverse processes. If I think about, oh, you've ever seen the meme about you think you're having a bad day at work? We've got one guy at a trailer shoveling dirt out of the trailer, and simultaneously there's another person. So one person's taking shovels of dirt out of a trailer. There's a second person taking shovels of dirt and putting it back in the trailer. For every scoop that gets taken out of the trailer, a scoop gets put back in. So that is what we mean by equilibrium. The forward and the reverse processes occur at the same rate. What happens to the amount of dirt in the trailer then if for every scoop that comes out, a scoop goes back? Nothing. It's going to stay the same. Again, if I think about this as an equilibrium, I'm going to divide this into two pieces. So let's see. I'm going to try. I gotta find this video. It's it's one of those, you think you're having a bad day kind of videos. So yeah. So you have this pile of dirt, right? And we've got person A who's taking the dirt and shoveling it out. You got person B taking and make them a smaller pile of dirt. Okay. Person B is putting dirt back in. Whoops. I don't know why I drew a dipole. I think I just get used to drawing dipoles. There's my little shovelly. Okay. So you have person two filling back in the same time it's getting taken out. So it's one of those, you're never going to fill up a hole if you're digging dirt out as fast as you're putting it in. So the person shoveling dirt out is matched scoop for scoop by the person shoveling the dirt in. And let's do this. Instead of just one scoop, let's do a bunch of scoops. Let's do 5 scoops. Maybe 4 scoops. That's what I got room for. Okay. So again, matching scoop for scoop. How many scoops go in, how many scoops go out, depend upon how fresh the two workers are. All right. So it's early, it's you know, cool temperatures, you got a lot of energy, you're gonna be moving some dirt, right? Now, what happens if, same idea, I still have my pile of dirt. I still have my pile of dirt. And I still have worker one with their shovel. And they're still taking 4 scoops out. Worker 2, they still have their little pile. They still have their little shovel. But now, a cute little kitty comes along. Okay, something interrupts the person who is scooping the dirt back into the pile. Well, what happens to the amount of dirt that this second worker is going to be putting in? It goes down, right? So they're going to get one scoop back in because the little kitty's so dang cute. This is what's happening with salt. This is what happens when we put salt down on the ice. My salt is the kitty. This blue shoveler is the process of moving the liquid back to the solid state. So over here, I have liquid let's not say moving, going into solid. Oh, I've actually got another pile of liquid being formed over here. On the other side of my really crazy drawing here, I've got the solid going to liquid. As long as those two processes are being matched scoop for scoop, the amount of solid is not going to change. So for every scoop of dirt from the blue pile in is matched by one scoop coming out of the solid. So the net effect is, and then it's going to form another blue. Don't worry about the piles. Okay? Just notice that one scoop goes in, one scoop comes in, one scoop is coming out at the same time. So the size of the black pile and size of the blue pile, it might not be in the same spot, but the size of the total amount of blue remains constant. This is where this idea of digging doesn't work. Okay. All right, so now what happens here? So the kitty's going to distract the digger. What happens to the amount of liquid going back into the solid? It's going to go down. Relatively speaking. Okay, so here now with the little distraction, we've got a new interaction. The rate of the liquid going back to the solid, the rate of dirt getting added back into the original pile goes down. The other person on the job is still being nice and efficient. Well, if person two moving the pile towards the left, what happens? The amount of material here has the net effect being transferred out. So the amount of reforming the solid is lower than, well, let's just leave it there. What's going to be the net effect? Okay, so the size of that solid will decrease. And will become liquid. Okay. So there's the story of my two shovelers with the kitty cat. Usually we're going to use an ionic compound. Liquid particles, because they're moving, are going to be able to interact more freely with this new ionic solid than the solid particles are. So the rate at which the liquid forms the solid decreases. The rate of solid forming liquid remains the same. Net impact. The amount of solid decreases. The amount of liquid goes up. That's our net impact. So it's not necessarily that salt makes it melt. It's really that the salt keeps the liquid from going back to the solid. So the freezing doesn't happen. If freezing doesn't happen, melting takes over. Potato, potato, six of one, half dozen of another. Um, Two ways of looking at the same coin. Yeah, sure. Yeah, sure. But technically speaking, it's the fact that it prevents refreeze. I like colligative properties. There's very little actually in chemistry that I don't like. There are a few things. There are a few things. All right, chapter 9. Chapter 9 is all about chemical reactions. So we're going to get into talking about chemical changes instead of talking about all of this physical property stuff. Before we get into some of the math stuff, there are two questions that I want to talk about. One is, how do reactions occur? And when you take more chemistry classes, if you take more chemistry classes, you'll be introduced to this idea as what's called a mechanism. So mechanisms are really just what is going on a chemical level that leads to the formation of different substances. We're going to follow what's called the collision theory. So how do reactions occur? Even our mechanisms piece follows collision theory. Collision theory really has three pieces. Collision theory is a set of statements to explain the required conditions for a chemical reaction to occur. Okay, that's awesome. Let's just talk about the conditions. Okay, piece number one. Reacting pieces have to hit each other. Kind of makes sense given that the theory is called collision theory. So the first piece is the reactant particles have to hit each other. Now, just hitting each other is not good enough. The second piece is that the collision has to have sufficient energy. If the particles don't hit each other, we're not going to get a reaction. If the reactant particles hit each other, the collision has to have enough energy. Awesome. The third piece. So the three aspects: collision, energy, and orientation. My son, he's not around, so I get to like do stories on my kid, which is fun. um Really, really picky baby in terms of eating. So in order for me to feed him, I had to be able to get the food to his mouth. In order to feed him, I had to get the food to his mouth quickly. All right. So really, there's a couple of things. I had to be fast enough or forceful enough to get the food to collide with his mouthy, right? So that's the sufficient energy, sufficient force. I also had to make sure that if I'm feeding him, I can't put the spoonful of strained peas, and I don't blame him for not liking strained peas. Sorry, anybody who likes strained peas. Strained peas, pea soup, it looks like the insides of a starfish. Sorry. Okay, anyways, so for me to feed him, I needed to bring together food and him. That's my collision. If I didn't bring the food in fast enough or forcefully enough, he wouldn't eat. Okay? He would deflect it. If he turned his head and I ended up putting a spoonful of peas in his ear, which I never did, that wouldn't work. All right. So, in order for him to be fed, for that reaction to occur, I had to get the peas to him fast enough slash hard enough. Okay. And I had to hit him in the mouth. Not literally hit him in the mouth, but insert spoon into mouth. For reactions to occur, I need to have the pieces that are doing the reaction come together. I have to be able to get the two pieces together with enough energy. If I don't get them together with enough energy, they will repel each other. And I need to make sure that where new bonds are being formed, that is where the collision is occurring. So you can think of it kind of as this feeding idea. To feed my kid, I had to bring together the two pieces. I had to bring together my kid and the food. My two reacting particles, kid, food. To get to feed him, I had to make sure that I got the food to him fast enough. If I didn't move fast enough, forget it. Right? He's going to throw up a block. He's going to reject it. Then I had to make sure that the food went into his mouth, not up his nose or someplace else. Right? So the reacting particles, I need to bring them together. I got to bring my kid and my food together. They have to hit each other with enough energy. If my reacting particles don't have enough energy, they'll get close and then they will repel each other. Third piece, in order to feed my kid, I had to get the food into the mouth hole. In order for two reacting particles to form new bonds, I have to get those atoms to be the ones that hit each other. If I don't have all three of those conditions, no eating.